Okay, so let's get started. So I'd like to introduce our next speaker. His name is Ben Weiss, and Ben is a computer vision expert and specializes in accelerating vision algorithms. So with that, I'd like to introduce Ben, come up and give his talk.
So, hello, my name is Ben Weiss. I'm working for CEVA as a vision expert in the customer solution group. Today's talk is about deploying visual SLAM building blocks into low-power devices like CEVA XM DSP. So, in this talk, we will briefly go over the visual SLAM building blocks and visual SLAM flow and what is it good for. What kind of challenges are raised when we implement it in real time, low-power device like CEVA XM DSP family, and how we can overcome those challenges using CEVA SLAM SDK. CEVA DSP is the worldwide leading licensor of DSP IP. We have DSP IP solutions for several signal processing fields like cellular, connectivity, sound, vision, and AI at the edge. CEVA XM is our DSP solution for imaging and computer vision, as well as deep learning, while NeuPro is CEVA's hybrid solution for accelerating AI at the edge, including a DSP and a powerful AI accelerator. So why do we need SLAM? Applications such as augmented reality or virtual reality and applications like indoor navigation requires a precise estimation of a device position and orientation. Solutions that are based on GPS or IMUs only have low accuracy and are not good enough for real products. In order to create a real immersive AR experience, we need to have a truly autonomous device. We need something else. We need SLAM. So what is SLAM? SLAM stands for Simultaneous, Localization, and Mapping. It is a process that eliminates sensor position and orientation in respect to the local environment. At the same time, the SLAM process creates and updates a map of the local surroundings. It is an ongoing process. Each new frame is positioned against the scene map and later can also help with refining and improving the map itself. The better the map becomes, the better we can find a new frame position. The better we estimate a new frame position, the better we can refine later on the scene map. Current leading SLAM algorithms were developed and designed for CPUs and requires huge computation power. It involves with many image processing and linear algebra operation that also requires large DDR traffic. Such intensive processing results in low frame rate and high power consumption. High power consumption causes battery drain that makes user experience very short, while low frame rate affects accuracy and hurts the user experience. How we can resolve these problems? The solution is to offload the processing from the main CPU into a DSP processor. Feature-based visual SLAM. We will go over basic SLAM processing models very briefly. Most SLAM algorithms implement three main models. The first model is tracking, a process that estimates camera location and orientation. It has real-time restriction and must keep high FPS, like 30 FPS, 60 FPS, in order to reach a good tracking accuracy. It mostly involved with fixed point operation, like in image processing, feature detection, extraction, and feature matching. The second model is mapping. Mapping is a process that estimates the 3D position of new and previous map points. Add new points to the scene map and refine available map points location. It is a semi-real-time process, not a real-time process. And it doesn't produce results every new frame and mostly involved with linear algebra operation using floating point data types. The third and last model is loop closure. This process refines global camera and map points. It is an extremely high processing procedure which requires floating point data type. All SLAM models that we reviewed shared some common building blocks. Let's review some of them. One group of function is image processing function. For example, image pyramid, feature detection like Fast9 and dog, feature descriptor, the popular one are ORB and freak, descriptor matching, and here we have two types of descriptor matching. We have matching on a frame, on a grid, and a grid search frame-based matching, and a point-to-point matching to create depth from the stereo sensor. For all of those, the dominant data type is 8-bit fixed point. Another big group of function is math operation. Linear algebra calculation that involve matrix manipulation and linear system solving. In this case, dominant data type is a single precision floating point and usually involves very big matrices, and many of them are sparse matrices. The computer vision DSP, the advantages and the challenges. CEVA's Vision DSP has some great capabilities for SLAM processing. Let's go over some of them. We have a strong arithmetic logic unit, very strong Mach engine, and very powerful floating point capabilities. In addition, a flexible and high throughput memory access and a dedicated vision instructions. CEVA's DSP is a very efficient processor with extremely low power consumption. On the other hand, there are some challenges for using Vision DSP for SLAM process, like small patch processing, like freak descriptor, for example, accessing non-consecutive data in the memory, random access, and sparse matrix manipulation. Another challenge is system-level challenge. First, we noticed that using data cache is not efficient enough for heavy SLAM processing. For efficient processing, we have to use local memory that allows zero latency access, and we must have a fine-tuned data prefetch. But using limited memory has some downsides, like image partitioning into tiles. We need to configure the DMA and monitor the DMA transactions. We have the processing overhead, and of course, DDR traffic increase. Integrating the efficient DSP to an existing SLAM application may raise the following complication: how to share complex data structure with the main CPU, which will probably use virtual memory. How to collect, pack, and transfer data between the CPU and the DSP, and how to maintain synchronization between the two of them. For summary, efficient processing is not a trivial thing. Integration with an existing application requires specific handling. So how we can harness the advantages of Vision DSP? We need a software framework to overcome those challenges. And this is why we developed the CEVA SLAM SDK. Let's see how this can be done. The CEVA SLAM SDK SLAM acceleration framework requires the following. In one hand, we need powerful hardware like CEVA XM family. Efficient embedded software, tuned algorithms that works well on embedded DSP is the second part. and easy integration with existing application. This is the third item that we need to implement in SLAM SDK. CEVA SLAM SDK optimized for CEVA XM Vision DSP as well as NeuPro AI processor. Now let's take a look at CEVA Vision DSP. We have a powerful MAC engine of 128 16-bit MAC per cycle, a 32 floating point operation per cycle, wide memory access of 512-bit, very flexible random memory access up to 32 different addresses in each cycle. We will see later on how this comes handy. Flexible DMA designed for image processing task and a dedicated vision instruction set. So CEVA SLAM SDK includes many highly optimized SLAM processing functions or building blocks, all designed and tuned to work well for embedded vector DSP like CEVA XM. Some examples of functions are image pyramid, key point, and feature processing, and of course, linear algebra calculation for the bundle adjustment part. Let's take a look at those functions and see how we can make it better and faster. Let's take feature matching, for example. The first part of feature matching is transform the points from one keyframe to another. We need to select relevant candidates around each feature, calculate the matching score, the Hamming distance between one feature to other candidates, and select the best match. This is typically comparing, this process is a heavy process. Typically, we need to compare 200 features from one frame to 2,000 candidate matches in the other frame. It requires around 400K match operation. So this is a very intensive process. So what can be done? First, we should focus only on relevant candidates. Processing all features requires much redundant processing and data traffic to the DDR. We can take only relevant candidates, and by that reducing the cost by a factor of 8 or factor of 10. We will need to store the data in a way that will allow us to access or select only relevant data without explicit sorting. We need a smart data prefetch for each source descriptor. Another way is to use the DSP SIMD capabilities. Now, let's take a deeper look at the Hamming distance calculation. The processing has two different parts. The first one is Hamming distance calculation, and we have some other control and management code for selection and sorting. Let's take a look at the timeline of such a process. Hamming distance calculation is in orange, while other calculations is in blue. CEVA XM6 efficient Hamming distance calculation instruction can calculate 256-bit descriptor only in half a cycle. That's very fast. Okay, now Hamming distance is calculated very fast in the DSP, but now we are left with significant amount of management scalar code overhead. The solution is to extend the vector processing time by processing multiple descriptors in parallel. We can process 16 or 32 different candidates at the same time, and this way the vector processing time is much longer and the overhead is reduced significantly. Now we have efficient parallel processing, but we need somehow to access multiple descriptors in parallel. We need to access 32 different locations in memory in parallel. Notice that there is no a single data structure or layout that can solve this problem. We will need to access different groups of candidates in different parts of the calculation. For example, access the descriptor data of feature 2 and 5 in the red circle, and in the next time, we need to calculate feature 2 and 3 in the green circle. CEVA XM6 can solve this problem. CEVA XM6 includes a unique parallel load store mechanism to load 32 different addresses in a single cycle. Now let's take a look at the performance example. Frame tracking is most composed of the following steps: image pyramid, feature detection, and matching. CEVA XM6 powered by CEVA SLAM SDK can execute tracking tasks for 60 FPS, consuming only 86 milliwatt. Utilizing only a fraction of the DSP processing capabilities, leaving room for other activities. Easy integration is extremely important. We made a lot of effort to offer those capabilities for the customer. CEVA SLAM SDK is easy to integrate with existing application. It's based on common APIs, making the integration fast and easy. It covers DSP or CPU communication, synchronization, and monitoring. It also takes care of the task scheduling, data collection, packing, and transferring between the CPU and the DSP. So CEVA SLAM is easy to use. You just need to plug it in and run it. CEVA can offer a full package of SLAM acceleration on mobile devices. We have a powerful and efficient hardware, as well as optimized and mature software functions. Robust and mature integration framework that allows a short time to market is also included in the SLAM SDK. For more information, you are more than welcome to visit our booth. Thank you very much for your time.
If you have any questions, please step up to the mic.
Hello, thank you for your talk.
Hello.
You mentioned you accelerate things like bundle adjustment.
Right.
I'm assuming you're doing single precision floating point.
Right.
How do you deal with the fact that single precision floating point with regards to bundle adjustment tends to require far more iterations to converge than double precision?
So we do have multiple iteration of a single precision floating point bundle adjustment in very efficient building block, and we can run multiple iteration in order to overcome this.
Okay. Okay, thank you.
Okay.
You said there are basically 3 steps: facial detection, then 3D
Mapping and loop closure.
Yes.
Yes.
Can you just give me how much time do you spend on each one of them?
So I can give you the full details in our booth. We have all the numbers there, and I think it will be more accurate to give it there, not here.
Thank you.
Okay, thank you.
Any other questions for Ben? So let me give him a plug. So Ben just recently moved to Mountain View, so he's local here. If you need more information, not only in the booth, but I'm sure you can get a hold of him here in Mountain View as well. So thank you, Ben.
Thank you.
Great presentation.